printing. Today we're talking about the fractal network of concrete and why it matters. So I've got 1, 2, 3, 4, 5 points here that, I mean, really, it's a coffee talk. Hey, Shia, it's a coffee talk. No problem, but don't forget to send me that direct message. So it's a coffee talk on something very scientific and specific that is all of a sudden relevant to the concrete industry, concrete and construction industry. So when we normally, and let me start off by saying good morning. My name is John. Please send me a message if you ever have any concrete questions, concrete concerns. And this, don't forget to like and subscribe. I would be remiss if I didn't say that. Morning, everybody. Ding that bell for notifications, blah, 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 blah. So on the fractal network of concrete, what I hope you get at the end of this is the teaser. What I hope you get at the end of this is you give a shit about a new technology in the concrete construction industry that should help make your job easier as a finisher, as the overall contractor, the superintendent, the ready mix provider, even the raw material provider. There are some great new technologies that connects these two worlds, and that's what I want to start into. So there's two worlds that we're talking about. When I went to school, when you guys went to school, I don't care if it was trade school or if it was civil engineering. Even if you're going for your PhD, more often than not, when we talk about concrete durability, when we talk about concrete longevity, we use the type of illustrations that you see here on the left, where it's a very rudimentary illustration of, let's say this is the concrete surface. Again, we're talking about the left side here where we have something that represents our pore, the hole in concrete, whether that's a crack or a void, something that creates connectivity, and we show it in this rectangular form with a decreasing radius. If we assume that this is a two-dimensional representation of a three-dimensional world, this would be a pore going into the concrete surface, and our radius gets smaller as we go deeper. Now, this very type of illustration was used to describe how pore water, as it evaporates from the surface of concrete, creates shrinkage based off of the equation P capillary equals 2 gamma cosine theta over R. Right? So very rudimentary, but with that we can discern a lot. You know, it's the great thing about engineering. As long as we're good with our assumptions, and we record our assumptions, not record, what's the word I'm looking for, Whitney? State our assumptions. You know, everything's kosher through our explanation. So whether it was shrinking, cracking, pore water distribution, and more, it is very common for us. Morning, Haley. It was very common for us to talk about concrete on this very rudimentary scale here on the left. But as it turns out with concrete, it's not as, I hate to use the word basic because I know the new generation uses that differently. It's not as rudimentary as we would like to portray it. You know, we're very lucky, and we should count our blessings that we work with cement. It allows us to do so much with such an educated guess. We really don't understand and really get to fully use the cement technology for all of its worth, but we're getting better and better at it. So with that being said, I want to introduce you to the image here on the right. Now take a moment and breathe that shit in, because I need to take a sip of coffee, but those two, the left and the right, it's the same freaking picture. It's taking a picture of the same freaking thing. It's just more detailed. And what we see here on the right is something called a fractal. And if you start reading some of these papers that you can get on what's it called for free, Google Scholar for free, this is one that I just printed out this morning. There's a fantastic one by Andrew Allen, I.G. Richardson on calcium silicate hydrate 1 and 2. That's the I.G. Richardson. But it doesn't matter. If you type in cement plus fractal network, you're going to find these awesome freaking papers on, you know, the hydrated molecular and microstructure of the glue that binds concrete together. Now, before I get into why, how, and how do we take advantage, all that jazz, I wanted to define fractal for you, because it's not just a cool picture, but a fractal is a curve or geometric picture, each part of which has the same statistical character as the whole. Fractals are useful in modeling structures such as coastlines or snowflakes. There's this snowflake animation on fractals that you gotta look into on YouTube. It's flippin' amazing, in which small patterns recur or progressively smaller scales in describing partly random or chaotic phenomena such as crystal growth, fluid turbulence, and galaxy formation. Oh, I just absolutely love that. So, as it turns out, when we take water and add cement to it, there's a chemical reaction between the dicalcium and tricalcium silicates. More so with the tricalcium than dicalcium silicates. But what happens is we get a dissolution effect with the combination of the water plus the cement. There's a breakdown of the parent material, the dried anhydrous cement, into this soup of calcium and silica. And when this soup starts aging, and this happens very quickly, it'll start spitting out some calcium hydroxide. That's the first precipitate to come out of solution. Now, as that calcium hydroxide, and you see it, it's lime. You know, you can see it when you have cement water that's been sitting around for a while. There's a crusty layer up top. But as that calcium hydroxide starts to pull out of solution, you get this supersaturated soup, this albondigas, this meatball soup. I feel like I'm trying to be like Tyler Lay and do cement hydration theater. But you do get this supersaturated soup of calcium and silica. And when your calcium and silica ratio gets somewhere between I think it's like a 0.72 and a 3.2, depending whose paper you read, it starts going through this gelling and hardening process. And please bear in mind, I'm dumbing this down a little bit, or I'm truncating it a bit, but it starts going through this gelling process where the calcium and silica starts converting into these nanosheets. And I had a teacher who once called them ham and cheese sandwiches. And if memory serves me correctly, you have the calcium oxide that acts as your ham and cheese, and the silicone bridging and silicone tetrahedra bridging and pairing tetrahedron, which I believe I call Dreherchitin. That's your bread, and since it's German, we should probably do a rye bread. But those are nanosheets. And on a very, very submolecular, or not submolecular, but molecular type structure in the nanometer range, there is a repeating pattern to it. That's why oftentimes in these papers, you hear the term amorphous like crystal, which is a bit of an anomaly, or it's a bit strange to say that, because amorphous means random, and crystal, which means repeating pattern. You know, how do you have those two? And with hydrated cement, you have those by, at a very small scale, we have those ham and cheese sandwiches. They're about 10 nanometers in dimension, and they stack on top of each other. But because of the randomness, the inconsistencies, the cement or the parent material, as well as the water, as well as the kicking off of hydration and the building of certain layers, you get this random pattern of structural development. So imagine, if you will, that the calcium silicate hydrate sheets are like clay particles. And if you've never used clay particles, pretend they're pieces of paper, right? And those pieces of paper, when they stack up on each other, they go from being flat to being, these are my notes. Okay. Go being flat to being crunkled up, and they still start stacking until they start making these patterns. So when we see this pattern, it represents not just the pore water and the concrete. As we get closer and deeper into it, it represents the pore water that's in a bulk state. And as it gets closer to the backbone of our concrete composite, this hydrated cement matrix, we see this transition not just from pore water to hydrated cement, or our hydrated cement matrix of our concrete composite, but we see the transition go from pore water in a bulk state to water that is chemically reacting. Then we see water that is chemically bound. Then we see water that maybe is not even considered water anymore. It's chemically incorporated, and more than likely it can be considered calcium silicate hydrate and other developed phases, and then it goes into the hydrated cement phase. So again, to do that, on these different layers, to explain that on the college level, on the contractor level, it takes a little bit more time. And the unfortunate reality is we don't have the time to describe not just what a fractal is, but why people should give a shit about it. So I think I've gone over how the fractals develop, and imagine, if you will, this is what the hydrated cement matrix really looks like. Maybe not exactly like this, but this is the form that it takes in lieu of what we see on the left. There's a whole thing on the Mandelbrot, I think I'm saying that right, series, and he was a gentleman from, I don't know if it was MIT or if it was another organization. I think it was a private organization where he did a fellowship with, I think it was an IBM fellowship. Anyway, this is how fractals really came to be, or our calculation of fractals, where he asked the question, how did he phrase the question? How long does it take to walk the coast of Brittany? And the answer was, it depends. It depends if you're a human, depends if you're a rabbit, it depends if you're an ant. And that's what it turns out with fractals. And the difference between these two photos, the photo on the left, or the image on the left, is a human being walking the coastline, and the image on the right is an ant walking the coastline, where a fractal increases our perimeter because we get higher detail of what's happening we take a closer look. And the deeper we look, the more we find, especially with these chemical interactions, that there's a repeating structure, as we just talked about. So the last thing I wanted to talk about, and why this is so important, this was the teaser. Why is this information important for us to know now as opposed to a decade or more ago? And this all goes back to the new types of materials that we have in the concrete and construction arena right now. We have been using a lot of supplementary cementitious materials and fibers that reside really in the micron structure. Class F fly ash, silica fume, Class F fly ash more so than silica fume. But most of these materials, even our coarse fine aggregate, even our fibers, are on the micron macro scale. The newer materials, which have been around for at least 2 or 3 decades, but only in the last decade have they become commercially available, have allowed us to use nanoparticles that are effectively the same types of materials, but because they're on the nanoscale, it has a different impact. And that's what most of my PhD research was on. Funny enough, is not available online anymore. So I think we're going to try and create a link on our YouTube, or not our YouTube. What is that thing called, Whitney? Our website. So y'all can get that PhD. But nanosilica is anywhere between the commercially available stuff. Normally is anywhere between 3 to 100 nanometers. There's some products that sell 100 nanometers plus, but the stuff that I normally use, anywhere between 3 and 100 nanometers, and shoot, you can get stuff that's really, really small. And the reason why that's so important is because these nanosheets of calcium silicate hydrate, that superhero, that backbone of concrete strength, those nanosheets, they're when I say nanosheets, they're around 10 nanometers. Now, the overall structure, the fractal network, is on the micro scale. So for the first time in the engineering, ready-mix, contracting industry, all three of those, we can effectively manipulate the molecular structure of cement hydration, those thermokinetics, by literally pouring a pint glass into the back of the truck, spraying something onto the surface of the concrete, spraying something onto the surface of our flipping reinforcing bars. I mean, using certain type of carbon nanotubes, graphenes, nanotitanium dioxides, nanocoppers. I mean, listen, I'm a little bit biased because I've spent, I think, 15 years. What is that, a third of my life? Yeah, something like that. Wow, that's pretty good. A third of my life focusing on nanosilica. My favorite type is E5 nanosilica. It allows us to get more bang out of our cementitious buck. Any of the nanoparticles that I mentioned will help you get more bang out of your cementitious buck, out of your durability buck, help make your concrete tougher. With nanosilica, it specifically goes after increasing the degree of cementitious hydration by taking advantage some of that water that's still in a bulk state, or at least in a free state that has not been chemically incorporated, and the calcium hydroxide. And most of this is, well, John, we do that with fly ash, we do that with silica fume. But because it's on the nanoscale and it can effectively fit within this fractal network, what we see is this increase in cementitious dissolution. We have a... Something's happening. Something's happening. Can I just get like a thumbs up from somebody that you can still hear me? Who's still on? My screen was just going black to white. Hey, Whit, can you call Dad? Yeah. All right, I hope this is still going. Okay, thanks, Wesley. All right, so what we see from this nanosilica first, and this is where I'm going to finish it up with, this is why we care, is this increase in accelerated cement, or this phenomena called accelerated cement dissolution. So when we add cement to our bucket of water, like I said, we only get so much cement bang for our buck. We try to get more by increasing the fineness, grinding up our cement, but as it turns out, as the cement hydrates, not only does it hydrate into free space, but it creates a diffusion barrier by hydrating into the anhydrous cement, creating a diffusion barrier, or some call it a hard candy shell, M&M hard candy shell. So the problem is we get left with somewhere around 30 to 70%, depending on whose paper you've read, of unreacted cement, because that diffusion barrier, it just makes it harder for water to get there and kick off that reaction. What the nanosilica does is, because we have all these reactions, and we're getting into so many nooks and crannies, and we're already in this dissolved state, or this state 4 reaction, our parent material breaks down more to feed more of this hydration engine. And with the nanosilica, because we've got a pozzolanic reaction, it's a coupled effect from the pozzolanic and hydration reaction. The second thing is that pozzolanic reaction, which normally takes a little bit longer, it sounds like the officiant in our wedding, love, the rabbi at our wedding. You know, when John fell in love with Whitney, it was love at first sight. For Whitney, it took a little longer. That guy. But it's like hydration, cementitious hydration, and pozzolanic reaction. You know, John fell in love with with Whitney, and Whitney fell in love with John. Cementitious versus pozzolanic, slow versus fast. As it turns out, for John, he gets the best of both worlds with Whitney, because Whitney is more like the nanosilica, where it's an instantaneous pozzolanic reaction. So just like John, Whitney fell in love with me instantly because she was more of the nanosilica pozzolanic reaction. And Landit in 2012 said it was more like a calcium silicate hydrate seeding effect, because it happened so quickly. And there's some beautiful illustrations that he put together. And then that third and final reason, there's something called heterogeneous nucleation. And I love saying it because it makes me sound so much smarter than I actually am. And what it means is when there are small things that have a small force field on them because of their size, other things will want to grow on their surface. So when we talk about the growth of this calcium silicate hydrate, we often talk about it, from the cement into the free space. And this is almost what we're looking at when we look at our pores, is that the cement is the dominant thing here, and it's creeping into the free space of the water. As it turns out, that's going on, as well as the pozzolanic growth that we're talking about in that pore water solution, where there's not only alkalis, but there's those hydroxides that go through that calcium hydroxide in combination with that silica will have that calcium silicate hydrate development through pozzolanic growth. Now, because we have that fractal network, if we have a particle that's really, really big, it's going to be really, really hard for it to get in there. But because we have these nanoparticles, specifically nanosilica, it can fit into those fractal groups, those networks, and increase the efficiency of our hydrated cementitious matrix. Reduce permeability, reduce percolation, which is all related to, especially percolation, it's the connectivity between pores. What's his name from NIST? Edgar Bozzi wrote some great papers about cement, concrete, and percolation, and that's all related to our fractal network. And of course, percolation or permeability with that pore connectivity always goes back to durability, strength, longevity of our concrete, and of course, a lot of folks have related that back to the bang that we get out of our cementitious buck. So that's why we should give a shit about the fractal network of concrete. Hope you enjoyed that. I'm going to be attaching this picture, doing this as a YouTube video, and we'll be sending it out for folks to see it. Before I hang up, I'm going to be cleaning up over here. Let me know if you have any concrete questions about this that I can address now. And thanks for joining, folks. Y'all are awesome people.